let's calculate one last sampling distribution of a statistic, the standard deviation. And we'll continue with our same example of Farmer Fred's egg production. So, what is the sampling distribution of a standard deviation? The sampling distribution of the standard deviation is the distribution of sample standard deviations with all samples having the same sample size n taken from the same population. So remember, in our example, we had a population size of 3. The population were the 3 days of egg production. One day had 5 eggs, one day had 7 eggs, one day had 12. We have this very, very small population. And what we knew so far now is that the mean of the population was 8. We found that the population variance was 8.67. That was a rounded value. And now we want to find the population standard deviation. Well, remember that the standard deviation, the population standard deviation, is just the square root of the population variance, and we already have that. So we can just take the square root of 8.67, and again, this is going to be an approximate number of 2.94, and remember, these are eggs, not eggs squared now because we took the square root. Okay, so let's get our samples up here, the samples we dealt with before. We had 9 of them. Okay, that's 6. 3 more. Okay, and for each one of these we had calculated the sample mean. Recall they were, let's see, 5, 6, 8.5, 6, 7, 9.5, 8.5, 9.5, and 12. And for each one, we had calculated the sample variance. We had 0 and 2 and 24.5, 2 and 0 and 12.5, 24.5, 12.5, and 0. Okay, so this is going to be easy for us to calculate our sample standard deviations because we will just take the square root of s squared. And I'm going to carry these out, the ones that do go beyond the decimal place, to 1.4142, 4 decimals. Okay, the square root of 24.5, 4.9497. Okay, we already have the square root of 2. That was 1.4142. The square root of 0, of course, is 0. Square root of 12.5. 3.5355. We've done 24.5, that was 4.9497. 12.5, 3.5355, and 0 was 0. Okay, so as we've done before, we can now calculate the mean of the sample standard deviations. Okay, one way to do that is to add all the ones that we obtained up and divide by the number we have. And recall we have 9 samples. So let's see, we've got 0 plus 1.4142 plus 4.9497 plus 1.4142 plus 0 plus 3.5355 plus 4.9497 plus 3.5355 plus 0, all divided by 9. And when we do that, we get 19.7988. And this is approximately, well, let's see, 2.19986. And since when we did the population standard deviation, we went to 2 decimal places, so I'm going to say this is about 2.20 eggs. But now we're getting something different than we've seen with the mean and the variance. When we did the same thing for the mean and variance, we found the exact same number. 2.20 is not the exact same as 2.94. Okay, well, let's see what happens if we do the probability distribution for the standard deviation. So recall we list all the possible standard deviations. We had 0, we had 1.4142, we had 3.5355, and we had 4.9497. Those are all the sample standard deviations from our entire population. So what was the probability that we get a 0 standard deviation? Well, how many ways were there to get 0? And there were 3, right? We saw 3 samples that had a 0 standard deviation out of 9 possible samples we could pull. How many had 1.4142? There's 2 of them. 3.5355, 2. There were 2 of those. And 4.4947, 2 of those. Again, we add these up. 5 plus 4 is 9. So we've accounted for our entire sample space, and now our x times the probability of x. So that's 0, of course. And then here, I'm going to just go ahead and go to a decimal, 0.3143. That's when you multiply 1.4142 times 2/9. And 3.5355 times 2/9, 0.7857. And 4.9497 times 2/9, 1.0999. And now let's add those up. Sum of the x times p of x, and we get 2.1999, or approximately 2.20 eggs. So we got the same thing that we got using this calculation, okay, 2 different ways to get the mean, but we do see they are not the same as the population standard deviation. So let's make a note of that. So note, the mean of the sample standard deviations is not equal to the population mean. I'm sorry, to the population standard deviation. So we got 2.20 for the sample standard deviations And for the population standard deviation, we got 2.94. So we see that they're not the same. However, they're not that far off. But what we do say here then is that the standard deviation, therefore, is not an unbiased estimator. But why do we say that we're going to be using the standard deviation so much? And we have already used the standard deviation so much more than the variance. And that gets back to the units. The units on the variance are units squared. And the standard deviation, while not the same, it's not terribly far off. So we will be using the standard deviation as our measure of variation in the data. It is important to know, though, what statistics are unbiased estimators and what statistics are not unbiased estimators.